So I need you also. All right, cool. All right, so this is that problem, that last problem from the first practice test. So it said use the tables to evaluate this. If you try to do this by hand, what method do you think you might try, and do you see why that would quickly not work? Why can't you use trig sub? That would be the first thing I might think. What's kind of in the way? There's like an extra x there, right? That's going to get in the way of me trying to apply an identity. U sub doesn't work because the derivative of this has an extra term that doesn't have, right? So that sucks. So this is definitely would be a difficult problem. It'd probably be a multi-U sub kind of step thing. But this is why there's so many integrals that we can't easily do. So we do them once, and then we make a table of integrals to help us do them if I see them again. So if I look on the very last page of the book. So the whole purpose now for this kind of problem is find the form that matches what I'm working with. So what do I got here? I got this one line, so not any, there we go. So if I look at these, I can see that 114 seems to match the form of it, right? And this is really, the reason that this section is really important. Obviously, tables should make everything so easy, but for some reason they don't. And it's because we're still not used to thinking about the form something's in. And that should be something that's just repeatedly just hammered on throughout your math experience, is the form is what's important. And how can I tell? That's obviously in that form, because u in that case normally would be translated back to x, right? Unless it was some other variable that they gave us. But it could be any general function of. So it might be one u sub I do, and then it looks like this. And then I can apply this outcome to it and then replace u with what it is. You guys kind of with me? So u sub preserves the form of something, and the table of integrals is all about identifying what form it's in. So I know I've got a radical. I know I've got an x on the outside. I know I've got a single x and then an x squared. That's cool. Let's see. And then there's a 4 there, so then I know my a is going to be 2. Cool. So u is x, a is 2, and now I can just plug and chug and get what the answer is. So look at this behemoth. I can't quite fit it all in there. There we go. Yeah. That's yummy. Right? This is not something obvious. Right? But you guys get the idea? Once you identify, in this case, A and U, and some of these is going to be A and B and who knows what else. You have to identify what they are, and then you just plot them in the right place. So obviously we're not going to be doing a lot of integration using tables. But it's important to talk about how to use them, because normally once you go into whatever field you're going into, you're going to have either like a little pocket reference, or you're going to have a software system that does it for you, but you have to pick the form it's in. So you still have to understand forms of functions and how to identify them. So what I want you guys to do, and this is going to be really interesting. I think we're going to have to do this together, since 4 of us have a book. I know a lot of us have the online stuff, but so this first one here. Right. So what's the important parts of this? What do you think that it might show up in the table looking like? It would be, this doesn't really matter. It's just a constant. So it'll probably just be du over, yeah, a, probably maybe a squared. Because this looks like the way I would treat this. How would I do this by hand? This is actually one we could do by hand. We could do trig sub. So very often on a test, I might ask you to do something, bless you, by hand, and then ask you to look it up and verify it in the table of values. And I'll give you like a little copy of the table of integrals. So if you have the book, see if you can find that. Let's see. And the nice thing is they kind of group these according to their most important parts. So I want something that's got over u radical a squared minus u squared. So it's not going to be these. These have all got u's in them, linear. So those are not useful. These aren't good. These are pluses in the middle. No good. This looks promising, right? Because I got a 9 minus x squared. So it's a squared minus u squared. So if I look at 35, there it is. Cool. So u is x, a is 3. Cool. And you just got to pull the 3 out of the way, right? That's the one adjustment you have to make so that the form matches correctly. That was random. Okay. How are we doing so far? So if I had, for example, just to show you, I could write it up here. If I had instead, if I had this, that's the same form, because what can I do? U sub. Right? So again, it kind of if we're allowed to use tables, our approach changes just a little bit, because now our U sub is not meant to get it to the point where I can integrate it myself. My U sub is to get it to the point where it looks like one of these guys. So it's a little bit different. I'm going to make a U substitution. It's not going to help me out if I had to do this by hand much. But it definitely helps me out because it preserves the form so I can see what it is in here. So if I did u equals cosine, du is negative sine. So then I just need to put a negative in there. Am I a little too zoomed in? There you go. So then the form of this becomes negative integral du over u square root of 9 minus u squared. So that's exactly the form that this is talking about. You guys kind of with me? So that's how u sub could work with integrals. Your approach changes just a little bit because you're not concerned with making it something you can do yourself. You want to make it something that looks like what the table says. But u sub still does what it's supposed to do there. Okay. So what about this next one here? What do you think it's going to look like? What doesn't matter? The 6 and the 5, because I can just pull 6/5 out, right? So it's going to look like du, u, maybe like a plus b, u. You with me? Yeah, because these inside I can't really do much with. It might be du over u, 1 plus b, and then I would have to pull out a 3. You kind of with me? But I'm looking for something that looks roughly like this. So I know I want something with a linear piece on the bottom. So I want to go back to that linear stuff here. These are all linear stuff here. And I want a u down there with it, and then maybe an a plus bu. So yeah, I pretty much just didn't do it on purpose, but there it is. Yay. So the one thing I have to do to make this exactly like that is to just pull the 6 over 5 out. Then it's basically exactly that with a equal to 3 and b equal to 4, yeah. And then I just have to rewrite. So what would the integral be then for that? So it would be 6/5 times, 1 over 3 ln x over 3 plus 4x, good? Plus c, yeah. C. Alright, so how do you feel about that? I mean, obviously, it's much easier than doing it by hand. But for some reason, people always have trouble with that idea of the form you're looking for. So if I give you a problem like this, you know I'm going to give you one that's kind of direct, just to make sure you can use the table. And I'm going to give you one where it requires a U-sub to make it look like what it's supposed to look like. But I'll tell you, use a table of values to integrate this. I have to tell you that because it changes the way you approach it. It changes what you're going to make U equal to. You're going to look through the thing and look at a form and make U equal to something and see if it makes it look like that in the table. Okay, cool. How's that? Is it decent? Okay, okay. So even if you have the online book, you should still be able to access the reference pages through the ebook. So you should still be able to get to this. But if I'm you, if I'm going much further in math or into engineering, I always start looking for, maybe you don't have to get, I brought that Mamma Jamma red book that one day, didn't I? Remember I plopped that up here and it just had like 100 pages of integrals. So they have little reference books, little pocket reference books that it's really good to get a hold of that's got quick little integrations and quick little values for constants and stuff. And they have it specifically for electrical engineering or for mechanical engineering or whatever. So it's not a bad idea to look for those. Normally they're not that crazy expensive. That big Mamma Jamma dude was like $90 or something crazy. He's got a lot of stuff. Okay. So I didn't want to spend a lot of time in that section, but a little bit of time to show you how it kind of works. So you just got to jump into it and see how you feel about it. So I want to spend most of the day on section 7.7, which is really nothing terribly new. It just kind of helps us figure out how to handle infinite integrals correctly. Alright, so 7.7. Oop, this is approximate integration. Did I skip something? No, okay. Oh, 7.8 is where we do infinite intervals. So 7.7. Approximate intervals. And this is bringing back and modifying some of the things we did to first discuss integrals themselves. So when you first talked about antiderivatives, and then you talked about finding the area under curves, and then you hopefully proved that those end up being the same. The antiderivative does lead you to the area underneath. Thank God. That makes everything a lot easier. This is going to improve on that a bit to help us numerically evaluate integrals that it cannot do by hand. So there are quite a few integrals that we cannot possibly do by hand. One of them I've already shown you, like e to the x squared. There's a bunch of them like that. Where I could do this integral if only it had a what out front? X, because then it'd be just a simple u sub. Take that x away and then suddenly it's impossible to do. Unless you use an infinite polynomial approximation for d to the x squared, which we'll do in chapter 11 or something, when we get to series and sequences. So the idea behind this section is, if I did have to integrate this from 1 to 3, let's say. Right. So this thing, e to the x squared, is just going to grow really, really fast. So at 1, it's just going to be
0.
At 1, it's going to be e to the 1. Good. So 1 is going to be e. And at 3, it's going to be e to the 9th, right? Which is, insane. I'm going to approximate it with right there. So my scale is admittedly inconsistent. You guys with me? Just because I don't feel like climbing on the roof. So it's going to look very roughly like that. So I'm talking about that area there. Now, on one level, it should feel like we should be able to do this by hand. In fact, we've done this by hand before. We could have done this by hand when we first talked about what integrals are. When we did, what's it called? Starts with an R. Something sums. Riemann sums, right? So hopefully you went through that when you first learned calc.
Yes.
So we're going to improve on Riemann sums. Instead of using rectangles that Riemann sums use, we're going to use trapezoids. Right? And we might talk a little bit about an improvement on that. But let me see if you guys can help me out. Riemann sum-wise, if I wanted to approximate this using, I don't know, 4 rectangles. You guys remember this? What else do I have to tell you?
Endpoint.
Yeah, which endpoint do you want to use? So let's say using 4 rectangles, using the midpoint, just to be evil. So I made this not horrible. I could have made it 7 rectangles or something stupid. But how far do I have to go? 2, right? And I want to fit 4 rectangles in there. And I'm using the midpoint, which means my rectangle is going to be centered over the midpoint between things. The height of the rectangle is going to be based on the midpoint. So if I want to start at, where would I start at then? Yeah, so the first height, so how wide is each of my rectangles going to be?
1 or 0.5.
Yeah, so it's going to be b minus a divided by n, so it's going to be 3 minus 1 divided by 4, so 1/2. That's how wide each rectangle is going to be. Right? So the first rectangle will go from 1, you put a 2 in there, 1.5, and then from 1.5 to 2. So now just got to be careful about the only thing that the which point you're going to use, the left, right, or midpoint. It just tells you how tall the rectangle is going to be. Is this coming back? Sort of? Okay. So I want to do this first because we're going to build off of this. And if we really don't remember how to do this, I can't build anywhere. So if I would have used left endpoint, the rectangle would have been this tall. Right endpoint, it would have been here. I'm using midpoint, so it's going to be about that tall. So just to capture it on a rough sketch, it doesn't have to be perfect. It already is not perfect. I got E to the 9th somehow fitting on there, right? So then the next one's going to be about here. And then I got another one here. And then the last one's about there. Okay, cool. So if you recall, midpoints basically is equivalent to left and right and then averaging. Right? Because the midpoint kind of accomplishes that averaging in one step. So the midpoint really was the best thing we had at that point. So we're just going to make it even better. So let's see if you guys. I'm going to leave this open to you. Find the areas of those rectangles and then add them up. While I figure out how far to go with this. So, do that here. Well, let's just say, yeah, 1 to 4, we have 4 approximations, okay. So what's the area of this first little rectangle? Yeah, so you have to figure out, so this will be 1/2. So I can pull a 1/2 out. I might as well just pull a 1/2 out in front of everything. So that's the width of everybody. So now I'm just going to do f of x1 plus f of x2. Just pull a 1/2 out of everybody. Because all the widths of the rectangles are 1/2. So now I've got 1/2 of e to the 9/4, right, basically? And then I can make it into a decimal. Because what am I plugging in to figure out the height?
1.25.
Oh, 1.25, that's right, that's better. That's 1.5 there. So the midpoint here would be 1.25 thing. So it'll be e to the, oh, what is that? 5/4, so 25/16. Is that better? You guys probably just got the decimal, right?
Yep.
I don't blame you. Plus, and then I'm going to plug in there. Put this here, 1.5, 1.75, 1 3/4, which is 7/4, so 49/16. Start to see the pattern. If you guys got decimals, that's fine. Yeah.
Where are you getting this original?
So the function I'm using is e to the x squared. So for this first rectangle, the height is based on the midpoint of the rectangle, so it's going to be 1.25, which is 1 1/4, which is 5/4. So this will be f of 5/4, which is e to the 25/16. Cool. See how crazy it is? Ask a question. There it is. And then this guy, you start to see 5 squared, 7 squared, so I'll bet you anything the next one's going to be 9 squared, because 2 1/4 is 9/4, so 81/16. And the next one, of course, will be 11 squared, 121/16. Yeah. So there's an exact form of the answer. And now you just plug in the calculator and get decimals. So who's got that for me?
Which one? All individual?
The whole, no, just the whole, what it is.
17.2.
17.2? Roughly. Does somebody get it all the way out? Is that what you got? So this problem, Riemann sums, is just evaluating a function over and over and over again. You could pretty much always pull the width out because you're letting the width be constant. And there's a lot of flexibility in Riemann sums. You don't have to evaluate it at the same point every time. You don't have to make the widths constant, really. Because what would I do to make these equal to each other? What would I do to this to make these equal to each other? I wouldn't use 4 rectangles. I use an infinite number. So, because the symbol here is the limit as n goes to infinity of a sum. It is an infinite sum. Sum of an infinite number of rectangles. Is this, you remember that? Talking about that? Okay. So I'm going off of one person here, but hopefully, yes.
I can't see what the first e says. It's e to the what?
Oh yeah, 25/16. Yeah. So it seems to come out to 17.2. Now, of course, your calculator could just eat this up, and your calculator basically does something sort of like this. I don't know exactly which algorithm it uses, but it's an algorithm based off of trapezoidal rule, we're going to talk about in a minute, or Simpson's rule. So, you want to try it on the calculator, see what it says? My calculator is currently recording. I'm going to do it up here on the overhead. Just make sure we're all able to do this. I think I've done this once or twice before in here. I want to make sure you guys can all do this on the calculator. It's a really good thing to be able to do to check your work on a test. I went off of the only person that said something. So we're going to check it right now. Yeah. So kudos to the brave person who said something. It turns out to be wrong. Don't feel bad at all.
So, that 17 is, so it's e to the 17.
All right, let's see if that's the right one. Yeah, cool. All right, so if you put e to the x squared what's up? And now if I go second calc, number 7, integrate from, what was it, 1 to 3? Yeah, I get a little something different. Right. So let's try this. So we got 0.5 times e to the 25 sixteenths.
When you catch us at a gross,
How do you mean?
like, you know how the numerator on it's 25 and the next one's 49, why can't you just add a gross?
Yeah, they're not like terms. You can't add x squared and x cubed and get x to the 5th. So you can't just add powers. And then you'd have to be multiplying to add powers also.
I was going to say it's good in squares. Each exponent.
Oh, you didn't square each exponent. Okay. Plus e to the, oops. That's weird. I don't want that there. 49 sixteenths. I'm not used to the new.
You left out a parenthesis.
You did, 449.
This is awesome. All right. 2 more to go. Let's see. E to the, let's see, that's 5, so this is 7, this is 9, 81 sixteenths. Plus e to the 21 sixteenths. All right, that's much better. So the actual answer was 1,043 or something like that, right? Well, we got off the, and that's a numerical approximation the calculator uses, but it's a really good approximation because it's able to make as many freaking rectangles as you want, basically, because it can make those kind of calculations very quickly. So considering this is an approximation that we use only 4 rectangles for, we got really damn close. Yeah?
On tests, like how many decimal places do you want?
As long as you show me the exact answer, and then you do the decimal, I almost don't care what the decimal approximation, because I got the exact answer. I got infinite decimals then, right? But in general, if you're not sure, it's a couple places normally is a good idea. Okay. All right, so how are we doing there? Is that, I didn't pick the nicest function for plugging into the calculator, but I'm hoping that the process kind of comes back to you, right? Everybody should have done something like this before you talked about integration. So one way to kind of improve on this, so I said earlier that midpoint effectively, but not exactly, averages out the left and right endpoint approach. So if you take the left and right endpoint approach, you'll end up with, and if you actually truly average them, you end up with page 508, what's called the trapezoidal rule. So if I take the left endpoint dude, would be if I have some function, and I want to go from here, say from A to B. So the left endpoint would say, and the right endpoint would say, so this would be xi minus 1, well this would be x0 effectively, and then the right endpoint would start at x1. So I don't know if you guys remember that. Just it determines how tall your rectangles are going to be. So this first rectangle, if I use the left endpoint, it would be this tall. If I use the right endpoint, it would be that tall. And of course, you remember talking about overshooting, undershooting, and the midpoint kind of averages all that out a bit. Okay. So if I took these two, added them together, divided by 2, I'm going to average them, truly average the left and right endpoints. What I end up with is this expression here, trapezoidal rule. And if you think about it, it kind of makes sense. In the left-hand version, I'm going to count this here. In the right hand, I'm not. In both versions, I'm going to count all the intermediate steps. You kind of with me? If I use left endpoints, I'm going to use A. If I use right endpoints, I'm not going to use A. That's why this endpoint only shows up once. These are all repeated. They happen in both left and right endpoints. That's why they're all doubled. And then if I use right endpoint, I will count this for the last rectangle. But if I use left endpoints, I'm not going to count that. And that's why, again, same thing for the other side. That's why that's related to A, only gets counted once. That's related to B, it only gets counted once. Everything else is in both, so they get 2 of those. And if I cut everybody in half, that's averaging what both of them would say. The reason this is called trapezoidal rule is you end up, for example, in this first one, you end up doing connecting the corners with a straight line, which is really kind of cool. You end up connecting this with a straight line. So that's why it's called the trapezoidal rule, because now what do I have here? I have a trapezoid. I don't have a rectangle anymore. I've got 2 parallel sides, 2 non-parallel sides. That's a trapezoid. So that's why we call it trapezoidal rule. It's crazy. Okay. Maybe. So now, again, this is just a plug and chug situation. This isn't terribly hard to memorize, but I'm not going to make you memorize that. It's really just something that doesn't get directly used a lot. You can build this into a computer program, for example, but computer programs use more modified versions of this. So let's see. Let me give you one to try to use this on. It almost doesn't matter what I pick here. Let's see. I don't want to use e to the x squared again. Let's not do that. Oh, it doesn't matter, Jeff. Just pick something. Sure. So approximate this using the trapezoidal rule, using, let's just keep it to 4 trapezoids. one thing I want you to realize is this is a little different than rectangles. With rectangles, I use a side and the height. That's all I need. For trapezoid, what's the area of a trapezoid? Oh, shit. No, Jeff. Can you draw a trapezoid? So if I give you several things here, what's the area of this trapezoid? 1/2 the height times the sum of the bases. So I really want to overanalyze this for a second. Do you see how this is 1/2 the height? So that's kind of taken out because that's in every single one of these. And then the first bases would be, what did I delete? If I use it here, this would be a base, that's f of xo, and this would be a base, that's f of x1. You with me? So you can see at 1/2 the height, f of xo plus f of x1. That would be the first trapezoid. The next trapezoid would be f of x1 plus f of x2. And that's another way to see why there's double of some of these and not of others. So it's a little different than rectangles. I'm going to end up with 5 values in there, not 4. Because if I want 4 trapezoids, I actually need 5 sides total. That's the same as always. I was a little bit evil here, but you'll get over it. You'll be okay. You got calculators. So it'll be 7 over 4 times 2 times. Of course, where did I start? 2. Yeah, I've got to start at 2. Right. So I start at 2. What's the next one? Twice it, right? I need 2 of these. Yes, sir.
2 plus 7 over 4.2.
4 times 2, sorry.
Oh, okay.
Yeah, because of the 2 here. So this is 7/4, and then you have a 2 already down there. If I would have wrote 7/8, then I would have said, where are they? What goes here? Where are you? Say again, sorry? Yeah, 2 plus 7/4. I know the width is 7/4, so I start at 2. I definitely want to use both endpoints. So I start at the first endpoint, the A, then I add the width, so 2 plus 7/4, and you can use decimals. It doesn't really matter too much. Or not, I like that, it's even better. So 2 plus 7/4, 4/4 plus 8/4 plus 7/4, 15/4, good. I'll just keep adding 7/4 and you'll be golden. Yeah, 22/4. We'll just leave it like that. So there's 1, 2, 3, 4, and I'm going to have one more after this, right? Yep, 29 over 4. And thankfully, everything seems good because the next one would be 36 over 4, which is 9. Thank God, this is where we want to end. So that's a really good check in the middle. Is, oh good, I added right, I did my width right. Cool. Make those match. A tiny part of me that's OCD. And now it's really just crank it out through your calculator, right? There's not a lot of, I don't want to be inconsistent, but.
Why did you say they'd be 5 instead of 4?
Not 5 trapezoids. There's 4 trapezoids, but the first trapezoid uses both of these to calculate its area. So it's the fact that every trapezoid uses 2 of those to calculate its area. I end up using 5 values total. Does that make sense?
Yeah.
Yes, ma'am.
So you can use the calculator for this part?
Oh, hell yeah. Good God. Square root of 15 fourths. I mean, come on. And root 15 over 2 is nice, but it's, at the end of the day, I really want to know what this is, right? So there's not a lot of use. I know we did the exact value with the e earlier, but showing square root of 15 over 2 is not a lot of value for that, really. So it's fine to just go ahead and throw this thing in there. So you get 7/8 times whatever all this mess, the square root of this, the square root of twice the square root of that. Don't forget the twice. Yes, ma'am?
How come the middle ones you multiply by 2?
So 2 ways you can look at that. One way is the first trapezoid uses both of these to calculate its area, right? And then the second trapezoid uses this one again, and the next one. And the third trapezoid uses this one again, and the next one. So all the ones in the middle get used twice.
So that'll be the same for all these types?
Yeah, exactly. So the ones on the outside only show up once, because the first trapezoid uses that one, and the last trapezoid is going to use the last one. Nobody uses those twice. Yeah. That's one way to look at it, and I'll just stop there if that makes sense. Okay, good. I've learned one lesson. Shut up when it starts making sense. All right, so it's just a bunch of plug and chug into the calculator. What do you get? Say again?
32.13.
And is that after doing 7/8 times that, or before? That's okay. So 32 point. Oh, you did 7/4. Okay. After doing 7/8 times that?
Yeah.
So 16 point.
Before multiplying by 7.8 is 18.4.
Okay. So 16.07. 07. Okay. So go ahead, and those of you with the calculators, try to do this one in your calculator and see how close it is. Just like we did the one earlier. Put the square root of x in y1. Second calc, number 7 is integral. If you don't have a calculator, just stare at your favorite wall. Stare at your favorite feature on the ceiling.
16.11.
Oh, sweet. That's really good. 16.11, is that what you guys are getting?
Yeah.
Okay, cool.
Just doing it by
And the last little thing here, Simpson's rule. So what Simpson's rule does is, instead of using straight lines between, so one way to handle this is to use rectangles. So that would use just truly straight lines, horizontal lines across, so forth, right? So we improved on that a little bit. We said trapezoidal rule would come in and use, diagonal lines, so it fits a little bit better. With me so far? Okay. So then one further improvement is to realize that the function we're integrating is definitely not linear. Otherwise, why would we wasting time? We could then use geometry to get areas, right? It's probably curved, so we'll use approximating parabolas in the middle. This is what Simpson's rule does. So Simpson's rule, Simpsons did it. Simpson's rule uses these approximating parabolas. So it doesn't use a straight line at all. It doesn't use a horizontal line. It doesn't use a straight diagonal line. It uses a curve, exactly. In this case, a parabola, specifically to calculate it. I have just decided not to try to run through the derivation with you guys. It's on page 513. Derivation is kind of interesting. They do it here on page 512. So it's kind of nice to kind of run through it. And you can see why it ends up being the way it is if you run through the derivations. They take a general parabola and they integrate it across one of these from like 0 to h for the width. And then they go from there. Right? And this is how they get down to Simpson's rule. Simpson's rule looks a little bit like trapezoidal rule, but it's got something. Oh, get out of there. A couple of differences. So it's got 1/3 there, which might kind of make some sense a little bit. Yeah, it doesn't quite really just perfectly, but if you integrate x squared, you get 1/3 x cubed. So don't freak out about there not being any cubes in here. Thankfully, we don't have to have all that. So then you get f of x naught plus 4 f of x1 plus 2 f of x2, 4 f of x3, all the way to the end, 2 f of x n minus 2, 4 f of x n minus 1, plus f of x n. Woo! So, yes?
Why is it a 4F and then 2F interchange?
So when I do approximating parabola, so they have a picture on the bottom page 511. So they do these approximating parabolas, and the way that it's set up, let me see if they show you here somewhere. In the middle of page 512, they tell you what the parabola passes through. So if I'm trying to go from, so if you look at the bottom page 511, so I know a lot of you guys don't have the book, let me put this up here. So trapezoidal rule had those 2's because you had a lot of trapezoids repeating the sides that they used. So that's why I had a bunch of 2's in it. This one, oh, sorry, it's broken up. So if you notice the way that they build this, a parabola requires how many points to be well defined? 3, good. I love it. That's crazy. So a straight line needs 2. And that's the x to the first power. A parabola needs 3. A cubic would need, it's crazy, right? So if I knew 4 points that a cubic went through, I could actually figure out what that equation exactly is, as long as the points you gave me are physically possible for a cube to go through. Are you guys kind of with me? So, since a parabola needs 3 points, you actually use 2. Do you see how I don't have a single rectangle across? Let me see if I can get this over there. So instead of having like a rectangle from XO to X1 and another rectangle or a trapezoid or whatever, we actually have across 2 intervals, I've got a single polynomial. Because it requires 1, 2, 3 points to be defined. So what I use is I use those 3 indices, XO, X1, X2, for example, to define this one parabola.
So that's why it's delta x over 3.
Yeah, exactly. Good. Now the reason it's 4 is not quite as simple, and that's part of the, I didn't really, let's see. This takes, so you can see up here where they integrate the parabola from negative h to h, and they say from 0 to h, because of the fact that, looking back at this picture here, so if I have, where am I? Oh, all right. I like this. I love this. You ready? This actually relates to a question somebody asked me a while back. There was one problem in section 7.5 that was really impossible to do by hand. And it's because it was a little bit of an evilness. This is something that you learn in Calc 1 that you really don't see a lot of. And it's kind of just something you got to remember that's possible. But why would the integral of sine from negative a to a be remarkably easy? Symmetric in what way?
From the negative a to 0.
Odd symmetry. So that means whatever area is on the below 0 is exactly the negative of the area above 0. So if you're integrating across a symmetric from negative a to a, it'll be 0. So there was a problem in section 7.5, I think it was, where it was like 4x tangent of something over, and it's like there's nothing. Nothing would work. And it's an evil problem in my opinion, because you just had to realize, it's odd symmetry. So the answer is 0 because it was from negative something to something, right? Yeah, so it's just kind of evil to do that because you already have so many things in your head as far as what to check for that's really easy to forget about, right? So here, when I go to integrate this function, they realize that the bx integral from negative h to h is going to be 0. So that's why it doesn't show up here. Cool. And they do all this business here. Now here they're just figuring out what the actual values are, what the heights are. Right? So at y0 it's at negative h. So this is going to be the value at y0. That's where it is. So at y0, that's the value of the output here. It's going to be this. Where'd it go? There it is. So they figure out these values. So then they say, okay, so if I add up, and look up here. When you did this, you got h over 3 times this thing. Now one reason this derivation, so often in calculus and higher level math, you have to play with something a lot to figure out the relationships. So when you integrate that parabola up there, we could all do this. This is pretty simple to integrate this parabola. And just get here by just taking h over 3 out. So that's pretty simple to do this. What's not so simple is to realize that that expression is equal to some combination of these values. So if you had to do this yourself, it would not be easy. And the actual derivation of this didn't take an hour. It didn't take a week. It took a long freaking time. Right? So it just took time to figure out how things kind of work together. So what's really nice is this is what you get when you integrate a general parabola sitting there. You get this. Specifically, if you take these outputs and combine them in this certain way, you get something that looks very familiar. So now what's the whole reason of that? What's Riemann sums built on? How tall is each rectangle is based on what? Function values. So you can see what they're trying to do. They're trying to take that integral and rewrite parts of it in terms of function values. So then I can have the same kind of rule set up. I could just figure out the function's value at a certain point, in this case 3 points, plug it in. So this integral of that parabola that was sitting there ends up being dependent on the function values in this very specific way, and there's your 4 popping up. Right? So if I add this to this, plus 4 of these, I end up with this. You kind of with me? A little bit? So I really want you guys... Sometimes I think you look at that and you think that I'm going to ask you on a test to redo this or something. All right? I want you to understand the amount of work that actually went into this kind of derivation. We have it all sitting nice on a page. This does not tell you the history of derivating this. Right? There's no history here. How long did this actually take? How many pages of work did it really take? Not represented well here. But now that it's all done, we can look back at it and say, well, that's what they did. They did this. Yeah. But a lot of stuff went into this. But, I mean, if you look at it, if you do add these together, plus 4, because you only get 2c, right? And you need 6c. So then they were really smart. You said, let's add 4 of those guys. Sweet. But what I really want you to understand is I'm just trying to bring it back to function values. So then I have an expression that relates to the function values, because the function values are easy to get. Plug stuff into the function. Who cares what the function is? I can plug stuff into it all day long. Kick ass. So now instead of this ambiguous, you have to figure out A and C for this weird parabola sitting there, no, you just have to figure out these function values for your function. Thank God. Right, so now that you've got the general expression for one parabola, you add all the parabolas together, and that's why some of them have 2 and some of them have 4. You kind of with me a little bit? So that's a little bit of why, I don't want to run through the whole thing, but a little bit of why it ends up looking like this. And again, I'm not going to make you memorize this. Right? I can't remember if I had to memorize that back in the day. It seems familiar to me, but I don't think you memorize it. So on this section, all I really want you to get used to is plugging these things into here, because eventually when you get to whatever field you're going to get to, whatever software you use to actually do your integration, you're going to want to understand the subroutines that actually do it. You're going to want to understand how they're written. So I don't know, so a lot of you guys are going to go into engineering, right? And depending on what kind of engineering you're going to go into, you're going to want to be more or not have to be very familiar with that at all. With some engineering, you're going to be intimately involved with what the hell is going on in the software. You're going to want to know something about what went into it. And most subroutines in a program that integrate stuff use, not exactly this, but modified versions of these. Anything you learn can be modified to make it better for certain situations, right? Okay. If you have to take a course called numerical analysis, anybody know if they have to take that course? Cool. If you're not sure, maybe you do. That's where you learn really the exact algorithms that computer programs use, your calculator uses, and you actually run through some of them by hand. Newton's method. You guys did Newton's method last semester, hopefully, or whatever semester you took 1A. If you didn't, you're going to find your teacher and slap him. If it was me, then you missed that day. So I know. Okay. Slap. So look here. Here's one little simple, not adjustment they did, but you see what they're doing here? They said, there's the trapezoidal rule. There's the midpoint rule. If you take 1/3 what the trapezoidal rule gives you and 2/3 what the midpoint gives you, together they give you what Simpson's rule would say. You guys kind of with me? So you do these weighted values of these things. So in certain situations, the midpoint rule is better. In certain situations, trapezoidal rule might be better. In certain situations, most situations, Simpson's rule is better. But if you weight them, you can actually combine them and make them better. So that's one adjustment you can make. You can combine them in different ways. Average them out in different ways. Okay. I didn't want to get too deep in this, because you do a whole bunch of error analysis on this stuff. I don't think I tried not to assign any of that, so we'll see if I did. Okay. And what's really nice about this, I want you to realize this, and the same thing can be said about Riemann sum, is this gives me the opportunity to do something based off of observations. So I can observe the temperature, right? Very easily, just step out the door. Or I can observe water levels, or observe chemical levels in a pond, take observations every 5 minutes. You kind of with me? So then delta x would be 5 minutes. My f of x would be the observed chemical levels over time or something. You guys kind of with me? So I can then integrate certain physical properties over time, and I can see like how much greenhouse gases can come out, or how much chemicals are being actually put into the river. Right? Just by point observations. I don't need a function then. So this is good for integrating functions I can't integrate by hand, like e to the x squared, but it's also good when I don't even have a freaking function in the first place. I just have a series of observations. Because all I have to do is plug in the values in the right place, depending on which rule I want to use to approximate the interval. So that's kind of cool. That's even beyond hard functions to integrate. This can do it when there's no function at all. There's just y values, because that's what's this built off of? Y values. You don't need the function itself. You just need the outputs. Okay, cool. What made me think about that was, some of these problems just give you outputs. They don't give you the actual function, which is even better. I don't have to take the square root of 7.3. I just put the value that they give me in. Kicks ass. Okay. So 7, 6, and 7, 7. You just have to jump in there and try it out. You'll be so happy to know that I'm going to go a little bit further today. Really pushing my luck. But some of you guys already think I'm crazy and horrible, so I'm just going to keep going anyway. So I can't salvage that, so it's too late. Forgot about you. God, you missed all that. Yep. Seven, 8. I don't feel too bad about doing this today because it's nothing exactly new. The only new thing about it. Actually, let me do that. That'll be better. That'll make it what I want it. So, something we're going to learn later this semester, which we already kind of know, is that I can have an infinite sum, and it doesn't have to be infinity. 7.8. You guys realize that? It sounds weird. If I sum something up infinitely long, and not something, I don't mean add 2 to itself for an infinite time. That's infinity. But if I add, for example, if I add 1 over n, let's say, how do I say this? 1 over n squared. So for n equals 1, that's 1. For n equals 2, that's 1/4. For n equals 3, that's 1/9. If I add that up, the sum is not infinity. And one reason it kind of makes sense it might not be is because I can imagine adding like 1/10 to the n. This will be 1/10 plus 1/100th plus 1,000th plus. Now to make this easier, those are all just freaking decimals, right? 1/10 is 0.1. 1/100th is 0.01. So in the limit, if I do this to infinity, what will I end up with? Definitely not 0, because that's not 0, and then I'm adding stuff that's not 0 to it. So I'll get 0.11111 forever, right? Which is 1/9. Is that rain?
Yep.
That's awesome. I thought it was supposed to rain tomorrow. I didn't realize it was going to rain today. Rain is good. Yeah. So be really careful driving. That is San Diego snow.
I have practiced that.
Because I've learned that people drive as bad in that here as people in Virginia did in actual snow. So, just calm down a little bit. Alright. You guys with me on this? So for those of you still paying attention, so this guy, why does it make sense? This has a chance to be what's called convergent. Convergent would mean that the sum actually goes to some finite number. Is he all right? What's up?
He left his.
Oh, scheisse. All right, you should run out and close that. No, I think they're closing their windows.
Yeah.
They're open. Oh, okay. You are getting your jacket. We thought you left your window down. Oh, okay. There's no window to
It's just hot.
Okay, so I can ask myself for some infinite sum. I can ask myself, is it going to be convergent or divergent? Convergent means it comes to a finite number. Divergent would mean it's infinity. So obviously if I added 2 forever, I would go to infinity. That would be divergent. This would be convergent. This would be convergent, but we have to prove it later this semester. So this guy, the way you've got to be careful about to do this is I can't plug infinity into something, even though I see this all the time. I get 1 over infinity equals 0, which is neat. You can't do that really, right? You have to treat it with limits. So how do I do that integral? So of course, you'll start to realize that as we learn new procedures, we're going to be bringing in the new integral stuff that we've learned. What method would I have to use on this? By parts? Cool. So you would be X. This is the last thing we're doing, by the way. So the quicker we get through this, the sooner we can be out there. Doing whatever you want to do out there in the rain. Frolic in the rain. Frolic with no abandon. dV equals. So V would be. All right, cool, right? And this should be a classic biparts problem. If I gave that to you in a test, you should see that. Just know it's biparts. It's got everything that biparts wants. It's not U sub. If only that was a squared, I could actually do it. Biparts would be the next thing I think about. So then I get limit as t goes to infinity. UV. So minus integral v du, so the negative makes it plus. You guys see with me? Now realize what's going to happen here sometimes. What's beautiful limit rule that you know now to make some limits of ratios quicker? French medical place. Hey, all right. So you could use L'Hopital's when it's when you have these infinite limits. L'Hopital's totally possible. You just gotta be careful about when you're allowed to do it. If you're not allowed to do it, it means you should be able to get the answer. If you can't get the answer, you're allowed to do it. So finishing up this integral real quick. What do I get here? Yeah, minus e to the negative x. No squares in there, please, Ryan. Can't attack the exponent of that. So I get the limit st. Oh, let me put this up here. Limit st goes to infinity. Put a t in there. And what do I get when I put a 0 in there? Oh, yes?
Where's the other
What do I get when I put a 0 in there? Yeah, I get 0 here, right? Plus, minus the negative, so plus e to the 0, so I get plus 1. That killed myself. So the only have to figure out that it's this piece here. Why do I have an X there? It should be a T. Thank you. So that piece is easy. What happens when t goes is infinity for this? 1 over e to the t. Please let it be easy. 1 over really big? 0. This one I got to figure out. I could write this as negative t over e to the negative t. So that looks like I could use e to the t thing. So I can move that e negative t down. One thing I can realize is that's a bigger function than that anyway, but if I use L'Hopital's real quick, what do I get? Negative 1 over e to the t. So that goes to 0, so I get 1. So the integral of x e to the negative x from 0 to infinity is 1. That kicks ass. It's really neat. Not neat enough to keep you here any longer, so we are free to go. Thank you. Sure.
So is there any way, like, I know you have a break Tuesdays,
I never learned it. Okay. Yeah, so that's the kind of thing you definitely want to come see me. You're talking about Tuesday. So my normal office hours don't work for you, right? So you're looking for other times?
No, I think that might.
If the normal office hours work for you, come in during any of my office hours. I'm there. If not, if you email me a few times, and I can pick some that'll work for me.
Definitely be like
Okay. But yeah, sometimes local talk is huge though. I'm surprised they never teach it. Okay. So come see me. So if the office hours work great, if not, email me some other times. Cool. Oh, sorry. That's your curve score. The curve scores a little bit, and that's your overall average. Just like quiz and the test average. Cool.
So, although I just messed up in the final step, so I had to.
No, start here. So I never, I want to know what sine 2 theta is, right? So you have to use an identity, choose sine theta, cosine theta, and then you can figure out what sine is and cosine is. Yeah, cool.